Highlands academic physics class. Today we're going to be investigating circular motion, and circular motion involves certain things. So I want you to watch a couple videos and a couple demonstrations, and then watch how I demonstrate how to use the proper equipment to investigate the relationship at hand. Okay, so the first thing I'm going to do is play a video for you, and I want you to watch. And we're going to be able to explain why some of these things are possible.
Yeah, good. My name's Dave Walters, and I'm a stuntman who does tumbling, gymnastics and parkour. I'm attempting to run the loop, because I've seen people do it on a skateboard before, I've seen people do it on a BMX before, but no one's ever tried it on their feet, so it's been nice to be the first guy to actually run it. It looks a lot bigger than what I thought it was going to be. Yeah, I must admit, not the easiest thing I've ever done. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
Basically boils down to this centripetal force. You need to keep on accelerating. So you need to reach a certain speed. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour. That's it.
Okay, 3, 2, 1, go. 17. Easy 5 minutes. Somebody's showing that one back. Well, this one's it. I know I've said that 3 times now, but this one is it. But I'm close, I reckon I'm close. I'm getting close. You can't really go any further until you take the match out. Let's go for it.
Okay, so watching that video should make you start to think about lots of things in the real world that travel in circular motion. If you look around the room, we have a couple devices that are spinning and they're maintaining their circular path. So what sort of force causes things to stay in a circular path? Okay, I have one more demonstration before I'm going to show you how to implement the lab. I have a cup of water here, okay, and I have a spinning platform. I'm going to proceed to rotate this platform in a vertical circle, and you should expect for it to stay on the platform. Ready? So, nobody's getting wet. How about, do you think I could possibly spin it in a circular fashion also and not get wet? Absolutely. So, how much force did I need to exert, and what sort of things does it depend upon? So that's what we're going to talk about for the next probably 3 class periods, is we're going to do a lab that investigates the relationship between force, velocity, radius, and mass. So the first thing I'm going to do is I'm going to show you up on the screen the lab write-up. Okay, you're going to be given this tomorrow. There are two big ideas that we're dealing with here. The first one is that science understanding is developed through the use of science process skills, scientific knowledge, scientific investigation, reasoning, and critical thinking. That's what we're doing. We're thinking as a scientist as we do labs. The second basic concept that we have been learning about for quite some time is any unbalanced force or net force will cause an object to accelerate. So when it moves in a circular path, is it really accelerating? That's the question. And so we're going to find that it is. So when you come tomorrow, you're going to get some equipment. The first thing you need is a pair of safety goggles to protect your eyes. You're also going to need a graphing calculator. You're going to need a circular motion kit, and I'm going to explain what's in here in a minute. You're going to need a meter stick, and you're going to need a balance, and in addition to that, either a stopwatch or your cell phone app, okay? So the first thing we're going to do is we're going to open up our little packet, and I'm going to show you what's inside here. So the first thing you're going to notice is that I have a rubber stopper, okay? This is going to be the mass that you're going to be rotating. Here is a circular tube of which you are going to be spinning, okay? You have some washers. There should be anywhere between 20 and 25 washers in this packet. You also need a paper clip, an alligator clip, and there's probably a piece of wood, a little piece of wood in there to help the string maintain in the rubber stopper. Okay, so in the lab write-up, I would like you to read the intro before you begin, but the whole idea is that you're going to need to mass what one of your washers is. So obviously that's what I have the triple beam balance out for. So you're going to just mass the mass of one washer and record it in your data table right there. Okay? Now for the first part of the lab, you are going to maintain the radius of the circular path. So I'm going to explain to you in a second what we're going to do. The first thing we're going to do is we're going to pass this string through this tube. Okay? And then I'm going to pass the string through the rubber stopper. And I'm going to help it maintain its position by using this little dowel rod. Okay? So that way this string should stay taut in the stopper. So the next thing we're going to do is we are going to measure out a certain radius. And this radius is going to be maintained throughout part A of the lab. So I'm going to choose to do 60 centimeters. Okay? So from the center of the stopper to 60 centimeters, that's going to be my radius. I'm going to record that right here in my data table. 60 centimeters would be 0.6 meters, wouldn't it? Okay? Then the next thing I need to know is I also need to know what the mass of the rubber stopper is. Obviously, again, what the triple beam balance is for. Okay? So now how am I going to maintain this circular path as it spins around? Well, that's what the alligator clip is for. At the bottom of the tube, if you could look closely, I'm going to place the alligator clip on the string at the bottom of the tube. You can see that from the center of the stopper to the top of the tube is the 60 centimeters. Okay, now at the bottom of the string, I have to attach a paper clip. On this paper clip, you are going to proceed to change the weight that you are going to use as your force in the lab. So if you look in the data table, I have 1, 2, 3, 4, 5 rows. You have to go from no washers or a minimum of 1 washer to as many washers as you have in your packet. So I'm going to increment by 4s. I'm going to do 4 washers, 8 washers, obviously 12, 16, and 20. Okay? So I'm going to place 4 washers on the paper clip. Okay, and I will have massed it right. So I would be able to, if I put 4 washers by here, I could multiply 4 washers by the mass of 1 washer to get the total mass of the washers. Now how do I get the weight? We've done this in the past. It's the mass times 9.8. So that's going to be your centripetal force that causes this to rotate. Okay? So I'm going to go ahead and I'm going to place my washers at the end of my string on the paper clip. Okay? Now one of you is going to need time. Okay? You're going to need the time because it's going to be kind of hard for you to figure out how long it takes me to just spin this around one time. So what we're going to do is we're going to rotate it for 20 revolutions. Okay? So we're going to go ahead and rotate it for 20 revolutions. If I want the time of 1 revolution, I would divide this total time for 20 by 20 to get the time of 1 revolution. Now, to calculate the velocity, you could take 2 pi r, which happens to be the circumference that the stopper will travel, and you're going to divide it by the time of 1 revolution. Now, what's the proper technique to get this started? Well, the first thing you want to do is you want to start it with the stopper at the top of the tube. And what you're going to do is you're going to proceed to start rotating this. Now, I want that alligator clip to stay exactly below the tube. Once I get it consistent and not up inside the tube, and you can kind of see it's climbing up in there, I just want it to rotate freely as it goes around, okay? So I'm going to go ahead and start that again, and I want you to notice how I begin. So I'm just going to start from it in the rest position. I'm going to go ahead and proceed to use my hand to create the force to spin this around. Now, whoever was doing my timing could go ahead and begin timing and counting the number of revolutions until you get a total of 20 revolutions. Okay, does that make sense to you? I hope. Now, once you get your 20 revolutions, then to make it stop, what you can do is you can pull down on the bottom of the tube. Okay? That way you don't hit your eyes with the rubber stopper as you slow down. Now, horizontal circle clearly means horizontal. Let me show you what not to do. Okay, so as you start spinning this, whoops, that didn't work out too well, but science sometimes doesn't, right? I'm attached to my bracelet here. We have a technical difficulty. Okay, I don't want that there anymore. And I'm going to start to rotate this again. Now, this is not a horizontal circle. There are 2 things going wrong here. It's actually at an angle, and you can see where my alligator clip is. Okay? Zoom in on where my alligator clip is, and it's not supposed to be up inside the tube. So in order to get this to work, I'm going to slow it down, and I want to watch that alligator clip freely flow at the bottom. Now I'm going to do my best to maintain this path for 20 revolutions as my lab partners time the time it takes to do 20 revolutions. Remember what you need to do to stop? You just pull down on the bottom of the string. Okay? So therefore, you could go ahead and calculate, once you have this, your velocity. You're going to proceed to increase the number of washers, which will increase the mass, which will increase the weight. You're going to time how long each of those takes, divide by 20 to get your time of 1 revolution, and you can calculate the velocity. Okay? Now, when you go into the analysis, what you're going to do is you're going to utilize the graphing calculator. We're not going to use graph paper and a pencil. But you're going to plot the weight of the washers on the y-axis, that's this column, versus the velocity of the stopper on the x column. Okay? You're going to see a graph that represents the mathematical relationship. You're going to use the calculator to get the regression equation, and we're going to then figure out what the constant in the regression equation represents. What I want you to be thinking about is, what did you hold constant as you were spinning this rubber stopper around your head? Did you change the rubber stopper? I don't think so. Did you change the radius? I don't think so. So somehow those 2 constants in the lab have to play a part in the proportionality constant A. We have to determine how that figures out. Okay? So that's the proper technique to take your data. So when you come in tomorrow, I'm going to have one of you demonstrate what the proper technique is for the class before we begin, and answer any unanswered questions that you have about the lab and what your task at hand is. Thank you for watching. Have a nice evening.